Based on electronic configuration, F block elements we classified into two types. The first one will be 4F, lanthanides we are calling. Also we are calling rare earths. Atomic number 58 to 71. The position in the periodic table, third B group, sixth period. Whereas actinides, atomic number 90 to 103, third B group, seventh period in the periodic table. So lanthanum and actinium belongs to D block. Lanthanum, actinium belongs to D block. So now let us discuss electronic configuration. The general electronic configuration is Ns2, N-1, D, 0, 1, N-2, F, 1 to 14. But one important point I'll say you have to remember. You remember CGL. Already we discussed lanthanum is a D block element. What is this CGL? Cerium, G for gadolinium, L for lutetium. We have one D electron. Cerium, gadolinium, lutetium, we have one D electron. Lanthanum is a D block. So the lanthanum doesn't have any F electron. So this is electronic configuration you should remember. And gadolinium has maximum unpaired electrons. Promethium, PM, synthetic radioactive element. Remaining all are normal elements. Next, let us discuss general properties. Lanthanum does not exhibit variable oxidation states. Samarium is steel hard. Melting points of lanthanides ranges from 1000 to 1200 Kelvin, but exception is there. Europium 1612 Kelvin. Lanthanides in +3 are colored in both aqueous solution and solid state. Very, very important. Lanthanum and lutetium in +3, cerium in +4, ytterbium in +2 does not exhibit color due to absence of F electrons. Lanthanum, lutetium in +3, cerium in +4, ytterbium in +2, diamagnetic, and remaining all are paramagnetic, even they are colorless. So already we discussed in the case of neodymium, maximum unpaired electrons are there, therefore it shows maximum paramagnetic nature. This point is very, very important. So neodymium has maximum paramagnetic nature. IP1 generally 600 kilojoules per mole, IP2 1200 kilojoules per mole, whereas IP3 lanthanum, gadolinium, lutetium is low due to F0 configuration as well as off-filled, completely filled configurations. So next one, chemical properties. Lanthanide chemical properties are similar to calcium, but as atomic number increases, it is similar to that of aluminium. Very, very important. Now let us discuss. First one, lanthanides oxidation state +3, oxygen is -2. So lanthanum 3, oxygen 2. The charge on cation will be returned to the anion. The charge on anion is returned to the cation. So criss cross method we are calling, so we are getting Ln2O3, Ln2O3. So with sulfur also same thing, we are getting Ln2O3, Ln2S3. And with acids, so because most of the lanthanides having negative SRP, that is the reason the reaction with acids, they are liberating hydrogen gas. Lanthanides plus 3, halogens minus 1. So therefore we are getting LnX3. So reaction with water, they are forming lanthanide hydroxides, cerium hydroxide, lutetium hydroxide, etc. Similarly, reaction with nitrogen, nitrogen is minus 3. So therefore we are getting LNN, lanthanide nitrides. Lanthanide nitrides. Very, very important. What is misc metal? Misc metal. Misc metal is nothing but, it's very, very important. 95% of lanthanides, 5% of iron. What are the traces we have? Sulfur, carbon, calcium, aluminium. Sulfur, calcium, aluminium. Scal, sulfur, carbon, calcium, aluminium. So this is very, very important. Next one, let us discuss about atomic size, ionic size. Very, very important. In the case of F block elements, from lanthanum to lutetium, you see in their ionic size, in their ionic state, lanthanum to lutetium, atomic size is decreasing, you see. Ionic size is decreasing. The decreasing ionic size in lanthanides we are calling lanthanide contraction. Generally, this is due to the poor screening effect. Screening effect is less means nuclear attraction will increase. So therefore, atomic size will decrease. Therefore, the decreasing atomic size in lanthanides we are calling lanthanide contraction. So what are the effects we have? Separation of lanthanides is difficult. And zirconium, hafnium, neodymium, tantalum, molybdenum, tungsten. Zirconium, hafnium, neodymium, tantalum, molybdenum, tungsten, having almost similar ionic size. Zirconium 160 picometers, hafnium 159 picometers. This is because of lanthanide contraction. Basic nature, cerium to lutetium decreases. Very important question. Cerium hydroxide more basic. Cerium hydroxide more basic. Lutetium hydroxide is least basic. And similar contraction is observed in case of actinides. But one important question is there. Actinide contraction is always better than lanthanide contraction because of poor screening effect of 5F electrons. Next, let us move to the oxidation states. Lanthanides, common oxidation state is +3. Common oxidation state is +3. But here you have to remember cerium, terbium, dysprosium, pramotium, neodymium shows a +4 oxidation state in their oxides. One important question is there. Cerium +4. Cerium shows +4 because of the inert gas configuration, noble gas configuration. Cerium +4 is converted into cerium +3. It is acting like a good oxidizing agent. So therefore it is used as an analytical reagent, lab reagent. Whereas europium, ytterbium, samarium exhibits +2 oxidation state. Europium +2. In +2 oxidation state, it is getting off-filled electronic configuration. Eu +2 converts into Eu +3 because this is common oxidation state. Eu +2 converts into Eu +3 because of common oxidation state. Oxidation number increased, therefore it is acting as a reducing agent. In ytterbium +2, it is getting full-filled F subshell. lanthanum plus 3, lutetium plus 3, cerium plus 4, ytterbium plus 2, ytterbium plus 2 are colorless diamagnetic. Remaining all are paramagnetic in nature. Next, 5F series elements we are calling actinides. We are also calling after atomic number 92 we are calling transuranic elements. Position in the periodic table, 3rd B group, 7th period. Actinium to lawrencium, atomic number 90 to 103, belongs to 5F actinides. Actinium is a D block element. All are radioactive elements. After atomic number 92 we are calling transuranic, synthetic radioactive elements. Atomic radii, ionic radii in actinides also decreases. This is called actinide contraction. So electronic configuration, majorly you have to concentrate. You remember TPUNL, that is thorium. In thorium we don't have any F electrons. Actinium is atomic number 89, but 90 to 103 we are calling actinides. Here one important point we have to remember, this is 89. So in the case of thorium, in the case of protactinium, thorium we don't have any F electrons, that is very very important. Thorium, protactinium, uranium, we have 1 d electron. Similarly, lawrencium also we have 1 d electrons, and 7s2 is common. 7s2 is common. 7s2 is common. So this electronic configuration you need to practice. So next one is, let us go to the variable oxidation states. Why actinide shows variable oxidation states? In the case of lanthanide it's not possible. In the case of actinides is possible. The reason is the energy difference is very very less. Comparable energies 5F, 6D, 7S, almost the same energy. Electrons can move from one. Electrons easily we can remove. That is the reason they shows variable oxidation states. You can see here thorium does not show +3 oxidation state. Common oxidation state is +3. You check here, common oxidation state is +3 in all the actinides. So very very important, you need to focus neptunium and plutonium. Neptunium, plutonium, they shows highest oxidation state +7. Highest oxidation state +7. So here if you observe carefully, from Pa to Am, they are showing variable oxidation states. So this is about oxidation states. Next one is, in 4F gadolinium, in 5F curium, having the similar electronic configuration. 4F7, 5D1, 6S2, 5F7, 6D1, 7S2. So what are the properties if you observe? All are radioactive. Actinium, thorium, protactinium, uranium, except to this remaining all are synthetic. That is the reason we are calling transuranic elements. Common oxidation state +3, +4, +5, +6, +7 is also possible. Actinide contraction is due to poor shielding effect of 5F electrons. Properties if you observe, all are silvery white metals. So nothing is important in this. Very very important. Most of the ions are colored. Their compounds are basic in nature. Actinide forms oxocations like uranium oxide, plutonium oxide, etc. Paramagnetic in nature due to unpaired electrons. Paramagnetic nature due to unpaired electrons. So these points you need to remember. So next one, finally, let us discuss what are the applications of D block elements. MnO2, manganese dioxide is used in dry battery cells. Titanium oxide is used as a pigment industry. In UK copper coins were using copper coated steel. UK coins, copper and nickel alloy. Copper nickel alloy is used. Vanadium pentoxide is a catalyst in the contact process. Ziegler-Natta catalyst, very important. Titanium tetrachloride plus aluminum trimethyl or triethyl. Titanium tetrachloride with aluminum trimethyl, Ziegler-Natta catalyst. Generally it is used in polymerization of ethene. Iron is a catalyst in Haber process. Nickel is a catalyst in hydrogenation of oils. And Walker's process, we are using palladium chloride. Nickel is used in the polymerization of alkynes. And finally, AgBr, silver bromide, is used in the photography industry, and it is a light sensitive property. Because of its light sensitive property, it is used in the developing of the photography. So this is about F block elements. I hope everybody understood. Read the NCERT. Thank you one and all. Please like and subscribe. Thank you.